Hi. Two's complement is a method to represent signed integers on a computer, meaning that numbers can be positive, negative, or zero. It is a fundamental piece of knowledge for every programmer, especially if you are in the medium or low-level programming languages, and of course if you are designing hardware. If you are using signed integers in your program, and you probably are, you have to understand what those odd-looking numbers mean. In this video, we're going to understand what Two's complement is, why it is defined the way it is defined, how it works, and most importantly, have important intuitive insights about Two's complement. Keep watching. Alright, so representing unsigned integers on a computer is well known and almost trivial, right? Every bit has a weight. This is the base 2 form of the number. And if you want to think about the value of that number in decimal, you summarize all those weights and you get the value. Well, how are we going to represent signed integers on a computer? The first thought that comes to mind is to do something that is similar to what we're doing as humans. We are writing down the absolute value of the number, and then we specify if it's a negative number or a positive number. Well, turns out this system exists for computers as well, and it's called the sign bit or the sign magnitude representation. Assuming that we have n bits to represent our numbers, what we will do, we will sacrifice the most significant bit and use just n minus 1 bits in order to represent the magnitude of our number or the absolute value. And we will use the most significant bit to tell us if this is a negative number or a positive number, 1 if it's negative and 0 if it's positive. Obviously, with the introduction of negative numbers, we can now represent fewer magnitudes because we are now using fewer bits for the magnitude. Using n bits, you can represent 2 to the power of n items, and it doesn't matter how you represent them or what they are. It's just a matter of how many combinations you can create with n bits. And if you have been reduced to n minus 1 bits, you can now represent only 2 to the power of n minus 1 items, and you have the MSB to tell you what sign you have. So the total amount of items we can represent is still 2 to the power of n, but the number of magnitudes was cut by half, and now we have positive and negative numbers. If we look at an example, assuming we have 3 bits to represent our numbers, then if we have unsigned integers, we have all the numbers from 0 through 7, and this is 8 by total. 2 to the power 3 is 8. Now we want to introduce signed numbers using the sign bit method. Note that I have rearranged the numbers, so the negative numbers are up, the positive numbers are down, and the zeros are in the middle. And you can immediately note that the first awkward thing that we have here is that we have 2 zeros. And that's where the problem started. The founding fathers of computing wanted to use the same ALU, Arithmetic Logic Unit, which is the part that is doing the math in the CPU, for both unsigned numbers and signed numbers without adding new logic or instructions. Now, just to emphasize the kind of magic that we are expecting here, we have an ALU that was originally designed to handle unsigned integers, and it doesn't know the notion of signed integers. And we want to keep it dumb. This way, we can keep it simple. We don't have to add new logic or new instructions, etc. But we still want the math to work. And only later parts of the program, for example, when we do comparisons, those parts will have to be generated by the compiler with proper instructions that do care about the number being signed or unsigned. But at this point, addition and also some other operations that we'll see later do not care if the number is signed or unsigned. Before going forward into seeing how this magic works, let's first demonstrate to ourselves that this is really how things work. We are looking at a tiny program in Compiler Explorer. On the left is the program, and on the right are the instructions that the compiler have produced from the program on the left. And you can see that I've defined 2 unsigned int numbers, and then I add them together and return them. And on the right, you can see that this translates to moving the numbers into EDX and EAX, and then adding them together with the instruction add. Now if I go here and I remove the word unsigned, and I'm telling the compiler that now those are signed numbers, and you can see that there is no change in the binary product on the right. We're still using the add instruction in order to implement this. Now you may think that this is because I'm still using positive numbers here, but I can change to negative numbers, and you can see that it has nothing to do with the values. The only thing that is changing are the lines that are assigning the values. But you can see that we are still using just the add instruction, which means that the ALU will do the same thing that it was doing for unsigned numbers. Okay, with what we have now, let's go ahead and look at how 2's complement is defined and why. So here's how we define 2's complement such that this entire thing will work. The negative of a number is the inverse of that number, meaning we flip all bits, 0 to 1 and 1 to 0, and we add 1. And there are some limitations that apply, and we will get to them shortly. Let's see an example. If our number is 101, which is 2, represented by 3 bits, the minus 2 is going to be the flip of all the bits, meaning 101 plus 1 equals 110. That is going to be our minus 2. And indeed, if we add those two numbers, we get a 0 with 1 carry or 1 overflow. And this overflow is fundamental to how 2's complement works, and we'll get to that shortly as well. Before getting into why 2's complement is defined this way, let's look at a few facts that will help us later. First, if you add a number and its inverse together, you always get a full set of ones, depending on the number of bits that you're using, or alternatively, a full set of FFs if you're looking at it as a hexadecimal number. Let's see an example. If our x is 1010, then the inverse of x, where all the bits are flipped, is 0101. If we add them together, we get an all ones. And if we add 1 to this result, we get a 0 with a carry of 1 or an overflow of 1. And it's easy to see that it does not depend on the number of bits that you are using to represent the number. This will always hold. Given those facts, you can see why 2's complement is defined as it is. The negative of a number is defined to be the number that when added to the original number yields a 0. With the facts that we have just seen, we know that when adding the inverse of a number to itself, plus 1, we have a 0 with an overflow of 1. So it makes a lot of sense to define the marked part as our minus x. This way the equation at the top holds and we have what we need. If that rings a bell, that's no accident. This is actually modular arithmetic. In modular arithmetic, we have a number of integers from 0 to n minus 1, and then n is our modulus. N itself wraps around and is another 0 of the system, and every multiple of n is a 0 of the system. For example, let's look at the system where the modulus is 8, and hence we have the numbers 0 through 7. 3 plus 4 equals 7, like you would expect, but 3 plus 5 equals 8, and 8 is another 0 of the system. It wraps around back to 0. And 3 plus 6 is 1. Because again it wraps around, it's 9, it wraps around, but you have a remainder of 1. So numbers that are larger than 7 wrap around into the system to become the remainder of a division by n. In this case, 9 divided by 8 equals 0, but the remainder is 1. Therefore, 9 in the system wraps around back to 1. Or in other words, 9 modulo 8 equals 1. The negative of a number is defined as the number that when added to the original number yields a 0. And therefore minus 3 mod 8 equals 5, because 3 plus 5 equals 8, mod n equals 0. 3 minus 4 equals 7, because 3 minus 4 equals minus 1, and minus 1 mod 8 is 7, because if you add 7 and 1, you get a 0 in this system. This is why 2's complement is called 2's complement. The negative of a number complements this number to 2 to the power of n. And of course, 2 to the power of n mod to the power of n is a 0 in this system. So when we said that we are complementing the numbers to 0, and now we're saying that we're complementing them to 2 to the power of n, it's the same thing in this system. Great, so now we know why 2's complement is defined the way it is, how it works, and why it is called 2's complement. Now let's look deeper into the mechanics of how it works and get some insights and intuition about it. When looking at how a 2's complement number is being created, let's take an example. Assume we have this bit pattern as the inverse of A, and then we want to add the 1. What's going to happen is that we'll have continuously 0 and a carry whenever we have two 1s, and then this 1 continues to travel because again there is a carry. Eventually it will settle on the first 0 in the inverted number, and then we just take the rest. The only exception where the 1 will travel all the way to the left and we'll end up with a bunch of zeros and an overflow of 1 is when A is 0 and therefore the inverse of A is a stream of 1s. In all other cases there is a 0 in the inverse of A and therefore the 1 will settle somewhere. That means that whenever we start from A that has a 0 on the most significant bit at the left, then the inverse will have a 1, and this 1 will not be zeroed by the plus 1 except when we started from 0. And from here we get to a great property of 2's complement. And let's see an example with 3 bits. Despite the fact that it wasn't designed to have 1 at the MSB for negative numbers, this property still holds, which is very helpful because you can just glance at a number and immediately see if it's a positive, a 0, or a negative number. Go ahead and compare that encoding to the sign bit encoding that we have seen before, and just notice that I've changed the order of the numbers so that the decimal presentation will still make sense. Positives from one side of the 0 and negatives from the other side. So you can see that the positive part looks the same, but the negative part is mapped differently. Again, let's look at how many numbers we can represent this way. Here too, we can only aspire to have at most 2 to the power of n numbers, with n as the number of bits. But here we have only 1 0. So 0 takes up one slot, and then we have 2 to the power of n minus 1 negative numbers, which is half the range. And since 0 took one slot, then the positive range can only have 2 to the power of n minus 1 minus 1. It might be easier to look at it this way. Here you have, with each number, you can see its companion, and you can see that this extra negative number, also known as the weird number, has no companion on the positive side. That's an example with the 4 as the number of bits. And you can see the same phenomena. Here the weird number is minus 8. And again, we can only represent the total of 2 to the power of n numbers. Let's look at a few very interesting observations about 2's complement. What happens when we try to negate 0? This means that we have to flip all the bits in 0, which are all zeros, and add 1. This equals all 1s plus 1, which overflows, and then it equals 0 again. So that's great. If we try to negate 0, we get 0 back again. The weird number is always 1 with all zeros afterwards. Take into account that when we start from a positive number, larger numbers will generally have more 1s. So when we go to the negative number and we flip all the bits, we will generally have more zeros. Again, with the exception of the number 0, let's put that aside. So in general, the smallest number we can have will have a 1 at the MSB, so it will be negative, and then all zeros. What happens when we negate the weird number? We have to flip all the bits in the weird number and add 1. But the weird number is 1 and all zeros, and therefore flipping of all the bits will give us 0 and all 1s. When we add 1, we get again 1 and all zeros, which is the weird number itself. So you remember we said that the weird number doesn't have a companion on the positive side, so this is what happens when we try to get to that companion that isn't there. We get the weird number again. It's interesting to see how the bits behave when we go along the axis. Generally speaking, if you're looking at a positive number, the more ones that it has, and when those ones are more to the left, you get a bigger number. If you look at the negative numbers, you will see that the more zeros that they have and the more left those zeros are, then they are smaller. One other interesting thing to see is that if you're starting from the smallest number, which is the weird number, and you start going up, you can see that if you disregard the MSB that is showing that this is a negative number, you can see that first you have no ones, then you have a 1, and then this one moves to the left, then you have another 1, and then again to the left, and so on. Then you get all the way to -1, in which you have all ones, and then you kind of overflow and you get to 0. And then this continues. You go again to larger numbers, you have a 1, and then the 1 moves left, and then you have another 1, and so on. This kind of helps to just look at a number, have an idea how big it is or how small it is. All right, great. Now let's go and see another great feature of 2's complement. If you know 2's complement, you might be thinking that in order to calculate the decimal form value of a negative number, you need to first flip it to the positive number, calculate the decimal form of that number, and then add a minus sign. But actually, you can calculate the decimal form directly from the 2's complement representation if you assign the most significant bit a weight of a -2 to the power of n-1. When we want to think of a binary number as a decimal value that is easier for us to comprehend, we use the known method of multiplying every bit by its weight and then summarizing. When we interpret the number as a 2's complement number, a very nice property is that we can use the same formula, but now the weight for the most significant bit is going to be -2 to the n-1. Let's see an example. We're using 4 bits to represent the number. This is the formula that we have if that's an unsigned integer. So it equals 6. Now we have a 2's complement number. And this is how we will compute the value of that number. We get a -2. You can quickly check it, it works. This is -2. You can demonstrate to yourself that this property holds if you look at the smallest number. We have only the MSB, and the smallest number will always equal -2 to the power of n-1. Another example would be looking at -1. -1 will always be all ones, and therefore its decimal value is going to be calculated by the weight of the MSB times 1, which is just the weight of the MSB, plus 2 to the power of n-1 minus 1. This is true because if we are summarizing all the powers of 2 to the right of the MSB, we can use this formula. This formula states that if you are summarizing powers of 2 ranging from 0 to k, then the sum is going to be 2 to the power of k plus 1 minus 1. Since this holds, you can see that the MSB again equals -2 to the power of n-1. If we think about the more general case, and if we're using again this formula, we can notice that the weight that each power of 2 carries is equivalent to the summary of all the previous weights minus 1. So intuitively, if you want to give weights to all the powers and end up with a negative number, then we have to put all the powers on one side, but then something has to tip the balance, and it must be just a little bit stronger than the rest of the weights combined. Okay, now we approach a super important feature of 2's complement, and that is sign extension. Sign extension will allow us to enlarge the number of bits which we use to represent 2's complement numbers. And this is very important because it is done on a day-to-day basis on computers. Let's see what happens when we embed numbers from a system with a smaller amount of bits into a system with more bits. So we start with a system with just 2 bits, and those are the numbers that we can represent with just 2 bits. And now we have moved to a system with 3 bits. And you can see that all the numbers on the left, the positives and the 0, got a new 0 to their left at the MSB, and all the numbers on the right got a new 1 at the MSB. But besides that, numbers from the smaller system remained as is, except being extended by either a 0 or a 1 to their left, and then we have the new numbers added. Now we do the same drill again. We start from 3 bits that we have just seen, and we move to 4 bits. And you can see that the phenomena repeats. Older numbers get extended and new numbers are being added. But very importantly, every number that existed in the smaller system has the same value here, except that it was extended by either a 1 or a 0 to its left, depending if it's positive or negative. Yeah, so sign extension is extremely important. Let's spend 1 minute to understand why it will always work. We want to show that when the MSB, the most significant bit, is 1, also meaning that we have a negative number at our hands, if we want to extend the bit size of the number by adding another 1 to the left, the overall value of the number will be maintained. So when we do that, we have a new MSB which will now carry the weight of -2 to the power of n, and the older MSB now will have the weight of 2 to the power of n minus 1. If we use the same formula as before, this is what we get. But we can rewrite the calculation for the 2 leftmost bits like that, by taking the 1 out of the parentheses. But then we can also take 2 to the power of n minus 1 out of the parentheses, and inside the parentheses we have 1 minus 2. And therefore, this is the result that we have. But this is exactly the calculation for the original number that we had. And by induction, you can show that you can do that forever, and you can get to any bit size that you want. So the bottom line here is that sign extension works. For positive numbers, you add zeros to the left. For negative numbers, you add ones to the left. Once we have understood sign extension, we have a really great property that we can derive from it. Take a look at this number. It's pretty long and it's a lot of math to calculate all the weights and summarize, but you don't have to. You can calculate just this number, and the rest can be looked at as sign extension into a bigger bit system. This is -3 in a 3-bit system, and therefore it is also -3 in any bigger system when we sign extend. Alright, so we have talked about addition. Subtraction is going to be very similar, as you can imagine. How about other arithmetic operations? Let's start with an easy multiplication, which is multiplication by powers of 2. And this can be implemented by shifts. You do not need multiplication logic. And we will see that it works on 2's complement numbers still by using the same ALU that was designed for unsigned integers. Shifting a number to the left is equivalent to multiplying it by 2. Think about decimal numbers. When you add a 0 to the right, it's equivalent to multiplying the number by 10. So here the multiplication is by 2. But watch what happened here. Let's go back to the original number. We started with a number that has an MSB of 1, which means in 2's complement that this is a negative number, and we have shifted it like that, and now we have a 0 at the MSB. That can't be good. Just by multiplying by 2, we have converted a negative number to a positive number. Let's see that this isn't really a restriction. We're looking at 2 different systems. One is with 3 bits, and the other is with 4 bits, and we're looking just at the positives now. Just like in unsigned numbers, if we multiply a number that is too big, we will overflow the system. For example, on a system with 3 bits, if we try to multiply 2 by 2, we get a 4, which is not a number that exists in this system. And the threshold is here. We can safely multiply numbers that are under the half threshold without overflowing. And you can see that all those numbers have a second 0 right to the MSB. So we know that when we'll shift those to the left by 1 place, we will stay in the realm of positive numbers. Now notice that the overflow problem is not special to 2's complement. In unsigned integers as well, if you multiply a number that is too large, you will overflow and get a number that is bigger than the biggest number of the system. Now let's look at the negative numbers. The same holds here. Every number that is under this half threshold is allowed to be multiplied by 2. Any other number will overflow and give us an incorrect answer. And you can see that all the allowed numbers had another 1 to the right of the MSB. So we can safely shift left this number and stay in the realm of negative numbers. Now let's talk about division by 2. To divide by 2, we shift to the right 1 place. and then add a 0 to maintain the same number of bits. And of course, we have to take into account that we have lost something here. We actually did a floor operation on the result, and we have lost the remainder. But what happens when the number is negative? Now we have a 1 at the MSB, and when we do this shift and having this extra 0, we have moved from the realm of negative numbers to that of positive numbers. That can be good. The solution is to use an arithmetic shift right. An arithmetic shift right will sign extend the number after we shift it, like that. If the old MSB was 1, it will pad with 1. If the old MSB was 0, it will pad with 0. So this is what we need for 2's complement. And we have shown before that sign extension is essentially inflating the number to a bigger system without changing its value, so it works. A nice special case would be -1. On a system of any number of bits, -1 will always be the number that has all the bits set as 1. When we do arithmetic shift right, we get -1 again. Strange? Not really. We have to remember that we are doing the floor operation on the division. So when looking at positive numbers, we get the floor of the number divided by 2. And floor will always give us a smaller or equal number. The same goes for negative numbers. If we divide a negative number by 2, again we floor to either the same number or a smaller one. It's always to the left. So when we divide -1 by 2, the accurate result is -half, but -half floored is again -1. So it all falls very nicely into place. All right, we have talked about addition, we've talked about shifting. What about multiplication and division? So when we come to look at multiplication, if you restrict yourself to multiplications of 2's complement numbers that end up in a solution that is within our system with the number of bits that we are using, you are fine. But that is not the standard way to do multiplication. Unlike in addition, where the result could be at most 1 bit larger than the original numbers that we were adding together, in multiplication it could be up to twice the size of the multiplicand. For that reason, when we will do multiplication, we will sign extend our multiplicands to twice the size of the original system and then do the math in that system. For example, if we are multiplying 2 bytes together, that's 8-bit each, we will first sign extend them to 16-bit each, and then we'll do the multiplication and have the result in 16 bits. Well, what about division? Unfortunately, division cannot comply with the requirement that we had at the beginning to use the same ALU that was designed for unsigned integer math on signed integers. So we will need to add logic and instructions to the CPU in order to support division, but remember that not every CPU, certainly back at the times where this was defined, have division functionality. Alright, thank you for watching. I hope you've liked what you have seen, and I hope you have a much better understanding now of 2's complement. If you did like this video, please hit the like button and subscribe to this channel if you want to see more content like this coming up. See you!